Good evening, students. We have come again for today's interaction on Physics 303. I still remain your facilitator, Professor T.J. Abu. I've waited for some time and I have to start. Others will join. I'll move on. Remember that the last lecture we had was consequences of Lorentz Transformation. It was based on time dilation and length contraction. Today we are still going to go further into the consequences of Lorentz transformation on momentum and image. So we move on. What are going to be our learning outcomes? That's where we start. Our learning outcome will be that at the end of this unit, we should be able to derive the formula for variation of mass with velocity. We are going to the next room will be that see that there is there is a different formula for mass when in this modern or new physics, that is special relativity. That is one point you are going to make, not necessarily deriving it, although the derivation is there. So we should be able to perform simple calculations involving the use of the formula for the variation of mass with velocity, and discuss the concept of force and Newton's second law in the mechanics. This will take the form of that of mass, because you know that in Newton's law, second law, you have F equal to the force is equal to mass times acceleration, rate of change of momentum. And then that is in the relativistic case, there should be a different formula, and that of force, because we have that is Newton's second law, we have the change of form. So let's begin by going into the first one, which is variation of mass velocity. Now, what we are going to do is to consider the effect of very high speed, or close to the speed of light. Effect of it on the mass of an object, and if there is a change, if the mass has effect as a result of the speed being very, very high, then it will have consequent effects on momentum and the force that is acting on that object. So remember that the moment we talk about momentum always reminds us of Newton's second law of motion. And you see that this is Newton's second law of motion. There people E differential from dm over dt. We know that the dt is the acceleration, which is almost the same F equal to ma. But in differential form, we put it in this form. So, but our interest here, we are talking about effects that this mass is going to have when the speed is very, very high. So, when we look at it here, you see that mass, M is mass, and if that is the case from this definition here, we have that F is equal to mk, and the acceleration is F over m. That is F of this is F. Okay, this This is F. F over M. If you make acceleration the subject of the formula. But if we remember in one of the equations of motion, we see that B equal to U plus 8. And at this point, if time is tending to infinity, velocity is tending to infinity. So classically, if a constant force is applied on an object for a sufficiently long time, this velocity is finite. So, and as a result of this contradicts the theory of spatial relativity. So, the case of that, okay, let me go to the second slide. So, but the speed or the velocity of that object is the velocity of that object is not allowed to reach or exceed the velocity of light. That is where it's contradicting. So that at a very high velocity, something is wrong. Very high velocity is something is wrong. You can see that Newton's second law is faulty. So we ask ourselves, how do we get around this? But how about mass being a function of velocity? That means m is equal to mv. That means m depends on velocity. Mass depends on velocity, provided mv tends to 0 as velocity tends to 0. So if we pick up this assumption, we are allowed to investigate the basic law of Newtonian mechanics that will be like the preserve remember that F is equal to mv. So as a result of this, then if we now make that preservation in the relativistic range, which in other words, results from the law of conservation of linear movement, that is now our main concern here is this is the statement, or this is a diagram showing the proof or showing the derivation of relativistic mass. But here, this is observer root and observer O1. So they are moving at the glancing position. They are moving at the glancing angle. When they get to this point, each of them moves its ball. Each of them is one. When they throws it, you see that one ball will be going down to one. That is the ball from O1 and the ball from both balls will be in the direction. So, and you see, but what we need to have in our mind is that the two observers are in relative motion. And being in relative motion, they are in a very high speed. You can see they are in this direction. One is moving this way, the other one is moving this way. So the figure here illustrates it, which I have also mentioned that the observer 1 is carrying for 1, observer 2 is carrying for 2. So as we move on, as they move on, they are going to be at this, because our point of reference is the x axis. They are going to meet here, where each of them is their ball. Well, let me not bother you so much about that. And if they release their balls, then it means that the two balls has to be resolved. One or two of them have to be resolved, but we need to take care of one before we next one. So our main concern Our main concern is that we are not going to just, I'm not going to describe the density process, not going to describe the effects or graduation here. Our main understanding here is that when the velocity of when the velocity is very, very high, up to the closest speed of light, the mass changes, has an effect. The mass is no longer m. It's no longer m, but will have another effect. Have an effect. In other words, the end result of it is that that mass m be expressed as mc or gamma mc, which is this gamma is the Lorentz factor, and you know that Lorentz factor is 1 over square root of 1 minus that square, and you know that beta equal to E by C. So the analysis here was thinking that the first of all, the motion of the mass from the observer 1 will be analyzed, and that of the observer 2 will also be analyzed, because I've already told you that each of them throws the ball perpendicular to the direction, the velocity, U naught. This V naught initially is far less than the velocity, ordinary velocity. So it's ordinary velocity, that is in the classical case, such that a glancing collision of the ball takes effect at point. That is this point I'm telling you at the point, which is midway to the observers, and then it rebounds with the same velocity at equal angles to the x-axis. So as seen in this case, you see that as seen by each observer, the path of motion of this ball, of their ball, is strictly plus or minus y. That is the vertical direction here. That plus or minus y. Here is plus or minus. That is, this is plus and this is minus. So plus or minus y. So that is where they are going to see the path of the ball. So, and the mathematics that follows in case of when we are now taking the conservation of linear momentum. The total, the momentum before collision and momentum after collision. For the end result of it, what I'm telling you is that at the end of it, if velocity is very high up to or close to the speed of light, the form of the mass is going to change, and we have a new expression for mass. That is the end of it. So the mass will now be, that's where I'm taking you to, apart from these directions. So the mass m will then be m naught over, or the mass m, just as I've written, I don't know why I now. Mass m is has an effect of this form. The mass m will be placed by gamma mc, where gamma is Lorentz factor and m naught is rest mass. That is the initial mass the object has. So you can see that the mass will have an effect. So it will have an effect. So in this case, you now see that the full expression putting the Lorentz factor here is going to be m equals to m naught over square root of 1 minus g squared over c squared. And if the mass has an effect, that means that the force will also have an effect. That means that also the momentum is going to have an effect. Every expression of force and momentum will change. No longer be for instance, force is not force is equal to ma. Force is equal to ma. This mass will now change into gamma mc. We are talking about the momentum. Momentum is equal to mv. That means that this mass is going to be replaced by this expression of mass or this one. So in other words, anything that, because the velocity is very, very high, the mass will have an effect. The mass is no longer constant, but it's changing with respect to its Lorentz value. So the mass has an effect. So in this case, we now call this M stick mass, and the M naught, just as I just said, is rest mass. So what are the physical significance of this expression? One, first of all, we note that by the symmetry of the problem, that is the symmetry of the problem, you see that O1 is coming and it's carrying E1, and O2 is coming in the opposite direction and it's carrying E2. So the significance of it that the observer 2 sees a similar situation and concludes that the mass of the ball E1 is also given by equation E.1. So both of them see the effect of the same thing. So they see they have a similar situation. Not only one of them is looking at it, but all of them are in their natural way of reference. Number 2, I don't know if you understood number 1. Number 1 is, you know, the case, or we know that by the symmetry of the problem, symmetry, just like you're having a mirror, this is a mirror. What you are seeing here, you are seeing you are the object here, you are seeing the distance. You see that the distance from the object to the mirror is the same thing as the distance from the mirror to the object. So if you are trying to draw even a graph, you draw a graph of something that you look at it, what is on the left, what is on the right. In this case, we talk about the symmetry, that is similar. So the case we are trying to show here is that for the symmetry of the problem, the observer also sees a similar situation, sees a similar equation as that. Similar equation that the mass being carried by V1 is also given by this expression. Two, at very high relativistic velocity, an object's mass, as seen by an observer, increases with the increasing velocity. So V is tending to C. In other words, mass is infinite. Mass, the relativistic mass becomes infinite. That means to say, if you look at this expression here, that means the ratio here is 1. If V is tending to C, the ratio V squared over C squared is 1. And you know that 1 minus 1 is 2. And any number divided by, okay, square root of 0, it's still is 0. And any number divided by 0 is undefined. So you can see that the mass will be infinite. Mathematics will take it that the mass will be infinite. So something has to be that the velocity must be less than that. But the significance of it now tells us that as V tends to C, M equals to infinite, tends to infinity. What this means is that the inertia of the object increases with increased velocity at the speeds. So the situation to illustrate this, because of the velocity of an object is because of that, the velocity of an object is prevented from reaching the velocity of light, just like the water had just explained, that something has to be done here that this velocity will be less than the velocity of light, less than that, not be exactly at it. So in that case, the mass and therefore momentum of an object cannot increase infinitely if it is taken to be like that. So if V is less than that, less than C, then you can see that something will. But here, we see that V tends to, as it tends to zero, equation here. As V tends to zero, this V tends to zero. V squared is zero. And 0 divided by C squared is 0. What we have here is 1. Square root of 1 is 1. So M naught divided by 1 is M naught. In other words, if V tends to 0, the relativistic mass is equal to V plus the mass. That's what it's telling us here. So we can see that as V tends to 0, M tends to M0. So it is instructive to examine the variation of M over M naught into V over C graphically, and that is illustrated in this case. So the ratio of mass and relativistic mass to that of rest mass is plotted on the vertical axis. The ratio of V with respect to C, velocity of light, is plotted on the horizontal axis. And you can see the behavior of it. So if this is increasing, the ratio from 0 to 0.5, you can see it has what? What it has here is the ratio is equal to 1 for M over M naught, the ratio of mass to M naught. The situation changes. This is approximately less than 0.5, but the situation changes here. You see an asymptotic curve of this line. See that as the ratio of velocity to that of the speed of light increases, you see that the ratio of relativistic mass to rest mass also increases asymptotically. But at the ratio, that is when the V is equal to, the speed of light, that is, the two of them has an equal value. We have this is 1.6. You now see that the curve tends to be tangential to this line, and it is tending to infinity. It's not touching it, but it is asymptotically increasing to infinity. And that is why we see that something has to be done, that this velocity has to be less than C. So this now illustrates the whole thing. So let's move further to now explain that. So as you can see from the graph, the mass is constant at M naught when V is small. Yes. For a velocity equal to 0, have 0.1 C. The relativistic mass is only 0.56 greater than the rest mass, M0. However, as V increases, the rest mass increases rapidly. At a velocity of 0.96, the relativistic mass is over 100% greater than the rest mass. It's obvious that the velocity of the object cannot be up to or exceed C. That is the illustration that is coming up from there. Now, having done that, we have seen that the situation of the mass has changed. That in the relativistic case, mass will have a very good expression of M equal to M naught to the square root of 1 minus V squared over V squared. So with this, you know, the momentum is going to also change. The momentum we say is mass times velocity. So in relativity, the momentum is going to change because the mass is no longer constant. The mass will now change with respect to time. Mass will change, momentum will change, and force will change. That's why we have momentum and force in the or making it. We want to have a different expression for momentum and that of mass in relativity. So let's dive in by, let me just express what we have there. Right? But this is just for you to, since you have known that, let me just, you have known that mass is expressed as m naught over 1 minus the square root of 1 minus b squared over c squared. Momentum, need to know that Newtonian and classical matrix, momentum is expressed as mv. So in this case, we substitute for this mass. And the mass is going to, the momentum is going to be m naught b over square root of 1 minus b squared over c squared. That's all this language we are speaking here. What we are speaking here is the same thing. That's what we are speaking here. Just telling you that here, if the mass no longer constant, differentiate mass, differentiate velocity with respect to time, giving mass the constant here, and then on this term, you give velocity constant and differentiate mass with respect to time. But we know that GMT does not vanish if the velocity of the body varies time. Yes. So the resultant force is always equal to the rate of change of moment. So in the next slide, we now have that here, what I have just done here, that provided m is given by our equation 2.1, momentum can be written as equal to m plus. For a very high speed, momentum changes. The expression for momentum changes, which is the last expression of it, and that is equation 2.2. So here, if in terms of components, we can write equation 2.2 in the form of components. That is here, momentum along the x-axis is m naught b x over square root of 1 minus b squared divided by c squared. This is 1 over square root of 1 minus b squared plus c squared, which is the Lorentz factor. For g of y, that is the component of the momentum along y-axis. It's the same, the only variation here is the velocity on top. And for z, it's similar to this, which is m naught b multiplied by Lorentz factor. So if you where v squared as expressed here, where v squared is vx squared plus vy squared plus z squared, that is the case of the activities. Because that looking at the component factors. So you have a change of form of the momentum. Change of form for the force, which we are going to form the force, but we are just looking at the momentum. So relativistic momentum has a different form, which is equation 2.2. But for classical momentum, we have G equal to mv, which is what we have done. So notice that for classical momentum, the result is mass times velocity. For relativistic momentum, you now have Lorentz factor multiplied by the rest mass multiplied by velocity. So we move ahead, and here is the case of that of the force. Change of force So by the Newton's second law, we can then write the same thing, which is the rate of change. The force is directly proportional to the rate of change of moment. And if this is done, look at the relativistic momentum. M naught is V over V is a vector over square root of 1 minus V squared is V squared. And that is going to give us V to G mv squared. Oh, no, not mv squared, mv. Mv is what? What is mv? Mv is momentum. That is the same rate of change of momentum with respect to the path. So here, in that case, the force is going to be expressed this mass. You change the mass into this. Becomes m naught v over square root of 1 minus b squared over c squared. So as we can easily verify from this analysis so far, if the net force acting on the system of particles is zero, momentum in the relativistic rate is conserved, provided the mass of a particle is given by equation P1, not mass. What we have is 2.2. So the momentum will be conserved based on that. So I think we have just explained one good thing about it, that the proper thing here, or what we have noticed here, is that at a very high speed, momentum is going to, a mass is going to vary. The expression for mass is going to vary. The mass is no longer constant, but now changes with respect to time. And an illustration is taken when we see two observers moving in the opposite direction, and when they are moving in the opposite direction, when they come at the midpoint between the two of them, they release the ball perpendicular to each other, the direction each of them is moving. So the significance of it now is that the person, the observer, the second observer, or each of the observer will see a similar situation. A similar situation is what? They will see that the mass they are having is a function of velocity. That means the mass will be expressed as m equal to m naught over square root of 1 minus b squared plus c squared. Or in another case, you just say is a Lorentz factor times the rest mass. That is it. So if mass has changed form in relativistic case, it therefore applies that momentum will also change. The expression for momentum will change, as well as the expression for the force. The expression for the force is also going to change. These are the three basic things we have got from here. So our next move is now to see, let's just pick an example. I don't know if that's what it's like. Okay. So here, I think I have the example. Okay, yeah, example. Example 1. In the example 1, the question is taken from your course material. I just use one of it. It's one of the self that's what you call it. It's left for you to solve, but then I think it's just an example. The question now says, how fast must a particle be accelerated by a linear accelerator for this mass to be larger than this rest mass? So That is question. How fast must the particle for this mass to be larger than this rest mass? So let the rest mass be equal to m0. In other words, the mass we are talking about is that the mass should be larger than m0 by what? By 6. So how do we do this to arrive at this point? We see that the mass is m, and it has to be mass, this mass was 50% of this rest mass. What is 50%? 50% is half. 50% is half. So if we have this m, here is m, that's m naught. So here is n, say 1 plus what? 1 plus half. And we know that half, 1 plus half is 1.5, which is 1 point. 1.5, that would be the smart point, 1.5. And that 1.5 is empty. And the 1.5 empty. So the mass n is going to be, because it's a 50% more than S mass. So we have this. So you can now see that the mass n is equal to 1.5 m0. So having known this, so you now see that 1.5 m0 is equal to m naught over, which is the expression for mass, because originally we know that the specific mass is equal to m naught over square root of 1 minus e squared over c squared. So if that is the case, you will see that this m naught, this mass we are looking at, then increased by 1.5 m. And that is why you have it displayed. So that here on the right is n and this n. Cancels each other. So that what we have left, and then 1.5 equal to 1 over square root of 1 minus. And we are solving for the velocity, because it says how fast. We are solving for the velocity. So the velocity here, we are going to solve will be that this is the expression. Let us look at the Lorentz factor here. The Lorentz factor is square root of 1 minus square is equal to 1 over 1.5. We get this 1.5. Okay. See how we got 1.5. But then the expression is inverted. That is, this is inverted. Take the reciprocal of both sides. We are going to have square root of 1 minus square root of 6 equal to 1 over 1.5. And when you take the LCM, so let yourself go ahead. So what is here? Note that 1 over 1.5 is 2 over 3. That means you have 1 over 1.5. And what I'm going to have 10. But just multiply by 10, multiply Okay, provide them. I have them. But 5 goes to this. 5 goes to this. That's why they are having it. Now, that is the pattern. Then, the little mathematics that we have to do here is square side. Square both sides, you are going to have 1 minus b squared plus c squared. That is equal to square root of 2 is 4. 3 is 9. And we take LCM on both sides. Okay, multiply this one by c squared. Multiply this side by 6 or the other. Let's see. Let's just see here. Let's see. We have minus b squared. Let me just pick it up on b squared plus c squared. B squared plus c squared is equal to 4 by 9. What we have here is LCM. LCM is what 9. It's 9 by 9 is 1. 1 by 4 is 4. Minus 1 by 9 is 1 by 1 is 9. And what we have here is 4 minus 9 is 5. Have minus 5 9. So remember that if you have cross multiply, I'm going to have b squared is equal to 5 by 9. Take the square root of square root on both sides. Take square root on both sides. That is here. Take square root on both sides and have equal to square root of 5 plus square root of 9 square root of 6 squared. So here, result in square root of you have square root of 5, square root of 5, square root of 9 equals, sorry, multiplied by square root of 6 squared. That is the result. So, but we know that C is 3.0 times 10 is 5 is that is our C, which is speed of light. So we can substitute it value. You see that velocity is approximately 0.745. C, okay, not the C was not I didn't finish it off, but if you multiply by this velocity, you can get a positive value. Also, although all of them are positive value, but leaving the answer in C as a function of C, we have 0.745 C. So that is the much it can go. That is how fast it must be. Particle be accelerated in linear accelerator. That is example 1. Example 2. Let me just finish it because our time is Gone. Let me just finish it. So the next second one is calculate the momentum of the proton moving at a speed of 0.906. So you can now see it that the momentum will change from mv will then become m. Recall our expression equation 2.2. Just m naught v over square root of 1 minus b squared over c squared. So in this case, what is something we don't know? We are talking about a proton. So the rest mass of a proton is 1.67 times 10 raised to the power minus 57 kilograms. What else do we need? So first of all, we calculate this denominator here, which is the Lorentz factor. So the Lorentz factor here is equal to square root of 1 minus b squared over c squared. And when it is done, it's given at 2.94. That is 2.94. But velocity of light, c, is 3.0 times 10 raised to the power 8 meter per second. So if we substitute for that, that means we have got this, the denominator here, which is going to be the momentum is going to be 1.67 times 10 raised to the power minus 27 multiplied by, that is the rest mass of proton, multiplied by the velocity, which is 0.906 divided by 2.9. So you can replace this velocity here of speed of light by 3.0 times 10 raised to the power 8. And if you use your calculator to calculate this, punch this, use it. For you to do that, if you punch it, then the result you are going to get is that the momentum is approximately 1.03 times 10 raised to the power minus 80 kilogram meter second, which is the unit of momentum. It does not change. So you can see that that's exactly what we are. That's exactly what we have, and this is the summary, which I think I have talked about it. That at ordinary speeds, you see, at ordinary speed, the Newton's second law remains in the form F equal to ma, and that is correct. But at a very relativistic speed, then that expression becomes contradictory. That means that form of equation is no longer correct. Because here, at very high speeds, the mass changes. The mass will have an effect. So that the mass will no longer be the ordinary mass, but it will be changing with respect to time. So let me see what I have here. So see, which is exactly what we have just at relativistic speed, Newton's second law in the form of this. But in the first case, classically we say that F equal to RT equal to M. It's correct. Classically, that is RT. But at a very high speed, this force Now we change from F equal to MD to DT, which is the rate of change of momentum with respect to time. And momentum is MV. So this M now change into form of M naught by 1 minus square C squared plus C squared. That is for the force. But for the momentum will also change. Because M has changed its form to M here. Because we know that the momentum is M. So this M by this expression of the mass. So here, in the relativistic rate, momentum is conserved provided the mass of the object is equal. So there's no contradictory statement here. The conservation of momentum remains the same, whether a classical case or the conservation of momentum remains the same, even though that the expression for momentum changes. There are other examples of X assignments. Say how fast. So just look at this here. How fast must an electron move if its mass must be equal to the rest mass of an alpha particle? So for electron mass of, okay, you look for the alpha particle's mass, alpha particle, rest mass of alpha particle. Now, a man whose mass at rest on the ground was to him. It's implied a rocket moving at the speed of this velocity on top of the side of M0, its velocity. Determine its mass while in flight as measured by an observer on Earth. Dead mass, not dead mass. What is the momentum of an electron? Find the less mass of an electron moving at less mass of an electron is moving at a speed of 0.876. Momentum. What is momentum? Speed is what we are looking at. Momentum is what we are looking at. Use that expression. But that's what you are assigning. Not so I'm done. Just practice. Like all these assignments that is given and practice the ones that are given to you. Three major things you are taking from this. You can ignore the derivation, but if you have time, just do the derivation. But what you know that if at ordinary speed, the expression for mass is okay, just mass. But at relativistic pace, the mass will have an effect. So it's going to be contradictory because at a very relativistic nature, the mass will be changing with respect to time. In other words, once mass changes, momentum is going to change, force is going to change. Again, we must note that the conservation of the momentum remains the same, whether in classical case or case. So that finally we see that the expressions for mass will be M not equal square root of 1 minus B squared over C squared. Momentum will also change because momentum M equals B equal to MT, that M, we replace it by the relativistic mass. And the force becomes the rate of change of momentum with respect to time. So if we put the expression for mobility, then we now have for momentum, we now have or expression for mass, we now have the change of the expression or formula for momentum. So you can see that each of them has different expressions in relativistic techniques. Relativity or relativity case we are talking about is at speeds close to the speed of light, not exactly to the speed of light. Because if we allow the speed to be exactly the speed of light, in other words, we are going to have an infinite expression of mass. Mass will be finite. So I am done here, and next time we will move ahead. So I'm going to upload it for you to go through it, download it, and practice it. Get it free. Thank you so much. Yeah. So for today, so next time, that will be next week. So from here, I'm saying goodbye. Thank you.